Welcome to Maths with EJD. In the last video, I started to talk about real analysis. We gave an introduction and we saw how real analysis is actually the backbone of so many things we've done. So many playlists I've even made on my channel in the past talking about calculus, probability, and all of these things, right? So this is the second video on real analysis where we talk about sets, logic, and quantifiers. Sets, logic, and quantifiers. I have a whole playlist on set theory, so you want to check that out. I think I have 14 videos on set theory. You want to check it out in case you need to catch up with that. All right, so let's move on to talk about this second concept in real analysis, talking about sets, logic, and quantifiers. So first of all, we'll start with the concept, with the idea of universe, elements, and membership. Universe, elements, and membership. Of course, in real analysis, we are talking about real numbers. Like I introduced in the previous video, we are basically talking about real numbers. And we saw that real numbers are made up of rational and irrational numbers. So where rational numbers are numbers that can be expressed as a ratio, you can see that ratio from the rational thing. So the ratio of two whole numbers, two integers, that is, and irrational numbers are numbers cannot be expressed as a ratio of two integers. And then we see that real numbers, the when you add rational and irrational numbers together, you get real numbers, basically. And I also explained that rational numbers are made up of natural numbers, which are normal counting numbers, and even integers, which are whole numbers, both negative and positive. Natural numbers are positive whole numbers, positive integers, right? While integers generally are negative and positive whole numbers. Now, here we're talking about inverse, elements, and membership, right? I mean, universe, elements, and membership. Since we're talking about real analysis, the universe here is typically the the set of all real numbers, which can be represented on the real number line. So the universe in real analysis is the set of all real numbers. And sometimes we go two-dimensional when you're comparing two different sets of real numbers. So in that case, we have an n-dimensional real number. So if you have two real number sets, that'll be R2 now. That means a two-dimensional real number. If you have three sets, that'll be R3. That's three-dimensional real numbers, meaning that you have three different sets of real numbers. So that is the universe in this situation, since you are dealing with real numbers. Then, after that, we talk about elements. An element is simply something that belongs to a set. All right. So, for instance, if you say X, this expression, this symbol, X in A, that X belongs to A. So this means X is an element of A, basically. So in real numbers now, we can say that 3 belongs to R. We can say -3/4 belongs to R. We can say square root of 2 belongs to R. We can say pi belongs to R, and so on and so forth. So like that. So these are elements of R. Then we can have some basic sets, right? So we have a set of natural numbers, which are just normal counting numbers like 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Then we have a set of integers. So Z represents integers. And like I said, integers are all whole numbers, either negative or positive, and 0 is also included, right? So all whole numbers, negative or positive, are integers. And then we have Q, which are rationals. I mean, you can't finish listing rational numbers, right? Then you have R, which are real numbers, and you have C, which are complex numbers. These are some basic sets when we talk about numbers. And I took time to define all the hierarchy of numbers in the previous video. You want to check that out, where I defined natural numbers, rational numbers, complex, real numbers, and complex numbers. And we saw that uh, natural numbers are subsets of rational numbers, and rational numbers are subsets of real numbers, while real numbers are subsets of complex numbers. So like complex numbers are the supersets of numbers, if you like to put it that way. Now let's talk about building sets. How do you build sets? You can actually build sets using the roster and builder notation. So the roster notation is where you list out the elements one after the other, right? So the roster, so A here for the roster type is you list out the numbers. But for the builder type now, you simply have, oh, X is an element of this R now, where X squared is less than 2. So in this case, now you're talking about all real numbers that satisfy this expression. So that simply means that X is less than square root of 2. X is less than square root of 2, and square root of 2 is 1.41, 41414141, and so on and so forth. So every number every number from, say, 0 to every number from negative infinity up to uh something somewhere close to, say, 1.4 or 1.4 something is actually part of this set. So you can actually list the items clearly, or you can have the builder type where the elements can be inferred. So those are the ways to build sets. You can use the roster method and the builder notation. Then we talk about subset, equality, and inclusion. So here now, I mean, we've seen some examples of this. So here you say A is a subset. A is I mean, this is the idea of this improper subset, meaning that A so A is a subset of B, meaning that all the elements of A can be found in B, or all the elements of A can be found in B, or all the elements. So this one under now means that A can be whatever, everything in A is everything in B. That's the idea here. So in this case, now we say for every X, so this same expression, now we say for every X, then X, for every X such that X is an element of A implies that every X is also an element of B. So this is what we have here. Okay. Then we also have A equals B. A equals B means that every element of A is also every element of B, with no overlaps. I mean, no extras, basically. So that means that A is a subset of B, and B is a subset of A. So if you want to prove that A is equal to B, you have to prove it both ways, that A is a subset of B and B is also a subset of A. So the two have to match. The two have to be correct for you to say A is equal to B. Okay, so these are already showing us how to, we know that real analysis is about a lot of proofs. So if you want to prove this now, this is how you start. You start by taking X, which belongs to A, and then you go all the way to show that every X in A is actually also in B. Then we talk about the idea of proper subset. Proper subset means that the equality part is not there. So we just have A is a proper subset of B. So the equality part is cancelled. So the equality part means that everything in A is also everything in B, no extras. But a proper subset means that everything in A is found in B, and B still has some extra above all the things that are in A. That's the idea of proper subset. So let's talk about some special sets. So in set theory, I dealt with some of these things already. So if you want to see that, you're free. So just check my channel, for that. So talking about special sets now. So we have that for special sets, we have empty set. An empty set is simply a set that contains nothing. So, and it is represented by this symbol, like some kind of O with a line crossing it. Then we have a power set. A power set is simply so the power set of A is such that when you have a set B, B is totally is a proper subset of A, right? That is a power set. Then you have Cartesian products. So Cartesian products is like you are working with two sets, and you take every possible pair of elements from A and B. That gives you the Cartesian product of A cross B. So that means every A and B, such that A belongs to A and B belongs to B. So if you have 1, 2 in A and you have 3, 4 in B, so the Cartesian product will be, so you take 1, so you have 1, 3, 1, 4, then 2, 3, 2, 4. That's Cartesian product in that case. All right. So then we have set operations and laws. So we have set operations and laws. So first of all, we have union. You can have the union of sets. The union of sets is every element that is common to both. Every element that you can find in either A or B or both. So if you can find it in either of the two, then it belongs to the union. So A union B is every X such that X is an element of A or X is an element of B. So if it belongs to A or it belongs to B, then it is automatically in the union of A and B, right? So you want to see that as maybe marriage, right? When a man and woman get married, they bring together everything that belongs to both of them. So they can have some things in common, but they also have some things that are not in common. But then they come together and pull all of these things together. That's a union. And that's why probably marriage is called a union. Then you have the idea of intersection. A intersection B is the collection of all X, such that X belongs to A and X belongs to B. So in a marriage now, so the attributes that the couple have in common, the husband and wife have in common, uh, these are the intersection. The things they have in common are basically the intersection, right? Then we have difference. Difference, A take away B. So when you have this slash means A take away B. So difference means that if you cross out everything that belongs to both A and B, whatever is left in A is the difference here. So this is like A minus B. So it is every X in A such that X does not belong to B. So if we take away everything that is common to A and B, whatever is left in A is the difference is A minus B. Well, and if you do B minus A, it means that if we take away what is common to both of them, whatever is left in B will be B slash A, right? B backslash A, that is. And we have complement. Complement means the complement of a set A means that everything if you take away everything that is in A from the universal set, whatever is left in the universal set, that is the complement. So it's more like a very good example is the complement of rational numbers in a real number are irrational numbers, basically. So A complement is equal to every X in the universal set such that X does not belong to A. So to get that, cross out everything in A from the universal set, whatever is left is your complement. Then there are some key identities we can also talk about. So key identities, we talk about De Morgan. So for De Morgan, we have A union B complement. So A union B complement is the same thing as A complement intersection B complement. All this can be proven. Then we have the distributive property, which says that A intersection B union C is the same thing as A intersection B union A intersection C. All can be proven. You have absorption, which says that A union A intersection B is the same thing as simply A, right? So if you bring whatever is common to A and B together, and you take the union with A, it gives you A back, because already A intersection B means everything here is in A. So if you do the intersection, whatever is left is going to be simply A. Then you have idempotent. Idempotent is something like A intersection A is equal to A. So A and they are the same. So they have the same. Their intersection is simply this. They are is still simply each them, so to speak. Then you have relations and functions. So a relation on set on A is a subset of A cross A. All right. So I mean, talking about relation, right? You're already saying you're bringing two sets at least together. So a relation on A can be a subset of A cross A. Then you talk about a function F. A function F, which maps A to B, means that every A belonging to A maps to a unique B that belongs to B. So you have two sets A and a set B. So it's more like say you're mapping. Yeah, I mean, I think marriage is very easy to use in this case. Every man is mapped to a woman in marriage. So marriage is a function. Lovely, I love this. Marriage is a function where every man is mapped to each man is mapped to a unique woman, something like that. Then you have the idea of injectivity, where f of x1 is equal to f of x2, which implies that x1 is equal to x2. So if two functions are equal, it means that their independent variables are also equal, right? Then you have subjectivity. When you say something is talking about subjective relations or functions. So every B belonging to B has some A which belongs to A. That's the idea of subjective. Then bijective is this combination of injective and surjective. So I think injective is known as one-to-one mapping, right? And here I think subjective should be onto mapping. Bijective is both onto and one-to-one. I think I clarified this in the set theory playlist. Then we have propositional logic now. So you have the idea of connectives. So this is negation to P, that's not P. So not P, that's the opposite of P. Then P and Q, that's P intersection Q, for instance. P or Q, that's P union Q. Then P implies Q, and P how do I put this now? P is Q and Q is P. I think there's a way this is called. I think if and only if P is Q. That means P goes to Q and Q also comes back. P implies Q simply means that P implies Q, but P can imply Q and Q may not imply P. But in this other case, P implies Q and Q also implies Q. Q also implies P. Then we have the idea of contrapositive. Contrapositive tells us that P implying Q implies that not Q, not Q implies not P, right? It is similar to that. So if P implies Q, it is similar to not Q implying not P. Then we have De Morgan that not P intersection Q, not P and Q implies not P or not Q. Now we have biconditional. So P implies Q and Q implies P. This means that P implies Q and Q implies P. That's like the two-way kind of thing I talked about. Then we can talk about predicates and quantifiers. So predicates P of X becomes a proposition when X is specified. Once you specified X, then the predicate becomes a proposition. So first of all, we have something universal, right? So if you say for every, so this symbol means for all or for every, maybe most likely for all X belonging to a particular X. So we have P of then we have P of X. Then we have the existential one. So I think this is there exists X belonging to S, for this P of X now. So these are like predicates. Then we have order of quantifiers. Order of quantifiers. Imagine this now that for all X, there exists Y in P of X comma Y, such that there exists Y for all X, for P X comma Y. Then example, for all X belonging to real numbers, there exists Y, which is also real, such that Y is greater than X is true. All right. For every X belonging to R, you have some Y, which also belong to R, such that Y is greater than X. So this is actually true. On the other hand, so there exists Y for all X, such that Y is greater than X. That will be false in that case, like that. Then we have negation rules now. So, the opposite of for all X belonging to SP of X. So the negation of this will be there exists X in S, which negates P of X, and this also goes like that. So then we have translating sets to logic now. So our topic is sets, logic, and quantifiers for the second video. So translating sets to logic. So you have X belonging to A intersection B. That implies that X belongs to A and X belongs to B, right? That means whatever X that belongs to A intersection B means it belongs to both of them. Then X belonging to A union B simply means that X belongs to A or X belongs to B. And this, so you can see the arrow is two ways now. So it also means that if X belongs to A and X belongs to B, then X belongs to A intersection B. Then if X belongs to A or X belongs to B, that means that X belongs to A union B. So if you want to prove that this is true, you have to end up here. And if you want to prove that the right hand is true, you have to end up with the left hand for each of them. Then if X belongs to the complement of A, that implies that it is not true that X belongs to A, because you have to take out everything in A before it can belong to this. Then if X does not belong to A, then it means that X belongs to A complement, like that. Then you have intervals on R. Yes, in the other video, I think I was talking about closed intervals and everything. So this is where we talk about this. So for intervals on R now, so we have an open interval, which means that so if you have an open interval AB, that means A and B are excluded from the interval. So open interval AB is such that for every X, we have A less than X less than B. For instance, if we have open interval 1, 5, right? Open interval 1, 5 means that 1 is not part, 5 is not part. So we only have 2, 3, 4. So 1 and 5 are excluded. That's what this means. But if we have closed interval 1, 5, that means closed interval AB implies that we are the collection of all X such that A is less than or equal to X is less than or equal to B. So closed interval 1, 5 means that we have if you list it out, it means we have 1, 2, 3, 4, 5. So unlike the first one where one of the extremes are excluded, here we have all of them included, 1, 2, 3, 4, 5. Then we have half open. So if you have half open, so this one is open below. So half open A, B closed, or half closed A, B open. So it means that so for half open, it means A is excluded. For half open A, it means A is excluded. For half open B, B is excluded. So if you have half open 1, 5 closed, it means 1 is excluded. So we only have 2, 3, 4, 5. But then if you have half closed 1, 5 open, that means we have 1, 2, 3, 4, but 5 is displayed. So we just have 1, 2, 3, 4. That like that. Then we also have raise. Raise things like this now. You have from A to infinity, comma, from minus infinity to B. These are raise when infinities are involved like this. Then let's talk about cardinality. So cardinality simply, I mean, from the basic idea of set theory, cardinality talks about the number of elements in a set, right? So we can have finite cardinality. So we can have bijection with 1 to n. So you know all the possibilities. Then we also have to talk about countability. So can you count the elements of a set? So here, in this case, we have bijection with natural numbers, bijection with natural numbers, e.g., you have irrational, no, e.g., rational numbers. So, I mean, this natural and rational gets me confused, right? So here now, for finite, if you have finite cardinality, it means that you can count from 1 to a given number. But on the other hand, for countable means you can't count. You can't count from 1 to n and it ends. But then you can, for instance, for rational numbers, we can count them and it just keeps going. But then for uncountable, we have no bijection with n, e.g., real numbers. Real numbers keep going and going because, of course, their real numbers are just endless because they are both cardinal, they are both rational and irrational numbers. So that can be a bit tricky. I think I also dealt with that kind of concept in the playlist on set theory. So here we have proof techniques with quantifiers. How do you prove with quantifiers? So when we talk about quantifiers, we are simply talking about things like for all such that for all there exists. So these two symbols, this is for all, this is there exists. So these are like quantifiers, to know how we go. So to prove for all x, so if you want to prove that for all x in something happens, so you take an arbitrary x and show the property. Then to prove that there exists x, you want to give explicit witness that it really exists. If you want to disprove for all x, then you just need to give counter example, right? If you want to disprove it. So if, for instance, if if I say that, which example can I give now? Okay. Okay, I mean, no idea is coming to my head right now, so let me just leave that. As we go on, we'll get clarity on these things. So real analysis statements. So if something is bounded above, so we say there exists M. So if we say something is bounded above, it means there exists a particular capital M such that, there exists a particular M for all X belonging to A such that X is less than or equal to M. That's what this means. So if something is bounded above, it means it has an upper bound. So it means that, so if you have a sequence, let's say you have a sequence like, a popular sequence I like to work with is 1, 1 over 2, 1 over 3. As it's going, you can see the number is reducing. 1, 0.5, 0.3333, then 1 over 4, 0.25, 1 over 5, 0.2, 1 over 6, 0.16, 1 over 7, 0.14, something. And it keeps going like that. So you see, it is bounded. So it is bounded below in that case because it approaches 0. That's being bounded below. But being bounded above that, it means that the number is growing and then it terminates at it's approaching a particular number at the top, right? So it's just like the absolute value of sine x at the end of the day, it stops at 1 for sure. So in that case, you can say absolute value of sine x is bounded by 1 above, like that. Okay. Then you have density of rationals. Density of rationals, you can say for all A belonging to B, there exists Q, which belongs to the set of rational numbers, such that A is less than Q is less than B. So that's talking about the density of rationals. So for every A that is less than B, then there's a particular value Q, which is the rational number that falls in between A and B. So that's simply telling you that if you like, pick any two numbers you like, any two numbers at all, any two numbers. Say if you like, you can pick 1.33 and 1.34. So between 1.33 and 1.34, you have something in between. You have 1.331, 1.332, 1.3323, and all that. So any two numbers you pick at all. Then you have injective function. So for all x and y, if you pick any two x and y, so you have f of x equals f of y, imply that x is equal to y. So if you pick any two x and y, if f of x is equal to f of y, it means that x and y are basically the same. That is injective function. Then we have limit of sequence. So for all epsilon, for all epsilon that is greater than 0, there exists a particular n. There exists a particular n, and then for all n greater than or equal to n, such that the absolute value of xn minus L is less than epsilon. So this is the idea of limit of sequence. So it means you take a particular sequence as the sequence is growing or reducing. So if you subtract the limit to which it tends from the sequence, the absolute value is always less than a particular epsilon that is greater than 0. Though it is pretty small, but it's greater than 0. So we have some examples here, which some kind of worked examples. I think it's better to name it worked examples. Let me just say worked examples. Okay. So some worked examples. Yes. So the first one, example 1, we have a set identity. A take away B union C is equal to A take away B intersection A take away C. So the proof, you want to show double inclusion via element chasing. So how do we do that? I mean, it's pretty lengthy, but you want to understand the logic behind it. Maybe I shouldn't even worry about explaining, but maybe I'll just run through once and go because it's a lot. All right. So the first thing is set identity A take away B union C is equal to A take away B intersection A take away C, right? So the first thing is you want the proof. We will show this by proving double inclusion. That is, A take away B union C is a subset of A take away B intersection A take away C, and at the same time, A take away B intersection A take away C is a subset of A take away B union C. So you have to prove it forward and backwards. That's the idea of double inclusion. So how do we go? So first of all, we want to start with the first side. So the part 1, show that A take away B union C is a subset of A take away B intersection A take away C. So first you pick a particular X. That's how the proof goes. So take a particular X. So you say let X belong to the starting point. Let X belong to A take away B union C. Take that. All right. And then you want to keep doing this until you arrive at the point where A take away B intersection this line. So by the definition of set difference, right? This means that because X belongs to A take away B union C. This simply means that X belongs to A and X does not belong to B union C, because by the definition of set difference, right? If X belongs to A take away B union C, it means that you cancel everything that is common to A and B union C, right? And then remove whatever is left, in B union C. So in that case, this means that X belongs to A, but X does not belong to B union C, right? So having done that, so once we establish this now, we are actually on. So by the definition of union now, so if X does not belong to B union C, that simply means that X so we have taken care of A not belonging to A. That one is taken care of. But then for this other side where X does not belong to B union C, so for X not belonging to B union C, this is equivalent to the fact that it belongs to the negation that X belongs to B or X belongs to C, right? If X does not belong to the union of B and C, it means X does not belong to either B or C. So X belongs to B or X belongs to C. It means if we have X belonging to B union C, this is what we have. But then this not element means negation. So this sign is negation. Don't forget this sign that looks like what should I call that now? It looks like a bench, something like an L that is upside down, or how do I something like that. So it means that this is the negation to the fact that X belongs to B or X belongs to C. And now that is taken care of, so we can then use the Morgan's law for logic and say, the negation of X belonging to B or X belonging to C is the same thing, is exactly the idea. Talking about the Morgan's law now. So it's the same thing that negation of X belonging to B and X not belonging to C. So that is what this implies. And if that is the case now we already know. So this means that X does not belong to B and X does not belong to C, because the negation of X belonging to B is X not belonging to B. The negation of X belonging to C means X is not belonging to C. So we can have that X belongs to A, X does not belong to B, and X does not belong to C. So, and imagine this is where we are still going to at the end of the day. So we can now say from X belonging to A and X not belonging to B, by the definition of set difference, we can say that X belongs to A, take away B, because X belongs to A, but it doesn't belong to B, right? So we can say, in that case, that implies that X belongs to A, take away B. Then for X belonging to A and X not belonging to C, by the definition of set difference, we have X belonging to A, take away C. And since we have taken care of that now, then we can then definitely say that since X belongs to A take away B and X belongs to A take away C, by the definition of intersection, we have that X belongs to A take away B intersection A take away C. Because if X belongs to A take away B and X belongs to A take away C, then it means that X definitely belongs to A take away B intersection A take away C, right? So because X is common to both of them. Thus, we can say that A take away B union C is a subset of A take away B intersection A take away C. So part 2 now, I mean, this can be really boring, right? So you just keep following the logic like that. You prove it forward, and then you have to also prove it backward. That is the idea of double inclusion. So this part 2, I won't bother about it, because it's like the reverse logic now. So here now you're starting from this other side. You want to show that A take away B intersection A take away C is a subset of A take away B union C. Again, you start by, the first thing you always do is let X belong to A take away B union A take away C. So once that is established, you can ask by the definition of intersection. This means that X is an element of A take away B and X is an element of, so it's just like the reverse of what you did here. And then you work your way back and then you finally say that, oh, since X belongs to A and X belongs to B union C, by the definition of set difference, we have that X belongs to A take away B union C. And then you can then say A take away B intersection A take away C is a subset of A take away B union C. And since we have both inclusions, so the right and left inclusion are there, we can conclude that these are really equal. So to prove equality is such a serious thing when it comes to this kind of thing. So you have to prove forward and backwards. Okay, so let's talk about the next example. So imagine this statement. We want to quantify negation. So statement, for all X belonging to real numbers, there exists a Q there exists a small letter Q which belongs to the set of rational numbers, such that Q that is a rational number, the square of that Q is actually equal to X that is also a rational number. So in short, we are saying that if you square any rational number, you also get a rational number. That's simply what this is talking about. And then talking about negation now. So so the negation of this is that for every X that is a rational number, then there exists X that is a rational number such that Q, which is also a rational, there exists X which is a rational number for all Q that is also a rational number, and such that Q squared is not equal to X, right? So it means that there's a possibility that the square of some rational numbers will not be equal to a particular kind of a particular kind of real number. So what are we saying here? For all X that is real, then we have a Q that is rational, where the square of the rational is always equal to real. Yeah, I think that's correct. Yeah, because I think that's correct. Then we said there exists a particular real number such that there exists a particular real number for all Q, which is rational, and then Q squared, that rational Q is not equal to a rational number, right? So let's look at the solution quickly. So first of all, we have the first statement, which says, well, Q squared equals X. Now, so in this case, this is a lot. So this statement claims that for every real number X, there exists a rational number Q such that Q squared is equal to X. This is false. For example, if X is equal to 2, then q squared is equal to 2 implies that q is root 2, or q is equal to minus square root 2. Neither 2 nor minus root 2 are rational numbers. So that statement is proven to be false directly. Of course, maybe it is true in some other situations, but at least if once you can find a particular case where it is not true, then you are good to go. So this statement claims that for every real number x, there exists a rational number q such that q squared is equal to x. This is false. For example, if x is equal to 2, then q squared is equal to 2 implies that q is square root of 2, or q is that, and these are not rational numbers. Okay, so they are clearly irrational, so that doesn't work. So that's for the statement now. So the statement is false like that. Then for the negation, so the negation, we now say that not for every x which is not, for every x which is real, there exists a q which is rational, such that q squared is x. So the opposite of that. So using the negation rule for the universal quantifier, this we negate the universal quantifier. So we have this. So using the negation rule, so we negate the universal quantifier such that we now say that there exists x which is real, and there does not exist a q which is real, so that q squared is equal to x. That's the negation. So using the negation rule for the existential quantifier, we have this. So we negate the existential quantifier to say that there exists x, a real x, for all q which is rational, such that q squared is not equal to x, because this negation is outside here. So this simplifies to the fact that there exists a particular real number for all q which is irrational. There exists a particular real number x for all q which is real, such that q squared is not equal to x. So at least we can find one, then that means you have negated the idea. So this statement claims that there exists a real number x, such that for all rational numbers q which is q squared equals x. So this is true now. For example, if we choose x to be 2, then for any rational number q, q squared is not equal to 2. I mean, that is established. Now we go for example 3. So for example 3 now, we have order, the importance of order. So we have, so for every epsilon greater than 0, for all epsilon greater than 0, right, there exists delta greater than 0, such that p is a function of both epsilon and delta, versus there exists a delta which is greater than 0 for all epsilon greater than 0, such that p is also a function of epsilon and delta. So the first is correct in limits and continuity. So solution now. So talking about order here, I think the example highlights the importance of the order of quantifiers. So we have this. So this statement says for every positive epsilon, there exists a positive delta, such that the property holds. In the context of limits and continuity, this generally means that for any given tolerance epsilon, you can find a delta that guarantees the condition that p is a subset, is a function of both epsilon and delta, e.g. the absolute value of f of x minus L less than epsilon when the absolute value of x minus c is less than delta is met. So the choice of delta depends on the value of epsilon. So, and in the second situation, we have this. So this statement says there exists a positive delta. So, I mean, all that in the context of limits and continuity, this would mean that there's a single delta that works for all positive epsilon values. This is generally not the definition of a limit or continuity, as delta typically needs to shrink as epsilon shrinks. Conclusion: the order of quantifiers significantly changes the meaning of a statement. So, in real analysis, definitions like limits and continuity, the for all epsilon, there exists delta order is crucial, because the existence of delta depends on the chosen epsilon. So there exists delta for all epsilon order is a much stronger condition that is usually not true for these definitions. So we need to understand that. So for all should come before there exists, instead of there exists for all. All right. For all there exists instead of there exists for all. That's the thing we have seen there, that order is really of importance. So common pitfalls, when we talk about set logic and quantifiers, you can forget to state your domains. So maybe it's, talking about real number, or so you can say every proof we have talks about them. We have to say that, oh, x belongs to real numbers or x belongs to rational numbers. So if you forget that, you can confuse whoever is reading your script or whoever is reading what you have written. So forgetting to state domains. So domains like real numbers, real number set or whatever. Then confusing inclusive versus exclusive or. So you have to pay attention. Swapping quantifier order incorrectly. So the quantifiers here are things like for all and there exists. So those are the two quantifiers. Then using one example as proof of universal. So you can't use one example as proof of universal, but you can use one example to prove exception. So once you can find one exception, that's good. But you cannot use one thing that works to generalize for everybody. But you can use one thing that does not work to prove that the law breaks down for sure. So mixing implication versus bioconditional. That's really important. So they're failing to provide explicit witness for existential. So, I mean, that case of proving that A is equal to B, though it can be quite boring that you have to do it forward and backward, but yeah, it still has to be done. Very important. And then you have some mini problem set here. So you want to try your hands on this. So you want to prove, first of all, that A intersection B all complements is equal to A complement union B complement. I think that's some kind of De Morgan stuff. Yeah. Then you want to, if true or false, for all X, there exists Y such that Y is X plus one. You don't do prove it logically. Is it true or false? Then there exists Y for all X such that Y is X plus one. Which one is true? Which one is false? You want to check that out. Then you also want to disprove the fact that for all n belonging to natural numbers, n squared plus 1 is prime. Of course, you can easily disprove that if you can find any n that you square and add 1 to it, and it doesn't give you prime, then of course you definitely know. I mean, I can already think of something like, say 3, is it 3 squared? Yeah, I can think of 3 now. 3 is a natural number, so 3 squared plus 1 is 10, and that is not prime. So you can easily disprove that if you can find but if you can find an exception, then the law breaks down. So show that Z is countable. That's show that integers are countable. Prove definition of injectivity. Translate. There exists a least upper bound of A, which is a subset of R. So you want to translate that based on the things we've considered. Then we have a proof checklist. Anytime you are doing a proof, it's important to take note of the following. So first of all, you never forget to define domain and givens, the things you have and the domain you're working with. Are you working with rational numbers? Are you working with real numbers? Or are you saying that a particular value X or Q or whatever belongs to real numbers or irrational numbers? Very important. Choose strategy. Do you want to go direct, contrapositive, contradiction, or cases? So one way to show that something exists is to show that one way to show that something does not exist is to show that its opposite exists, something like that. That's like contradiction. Then track quantifiers. So make sure you track your quantifiers, arbitrary versus witness. Things like there exists for all or for all there exist. Then translate sets. So you can translate between sets and logic as needed. Then state conclusion explicitly, whatever your conclusion is. So if you want, one easy one that we did is to prove that A is equal to B, prove that A is a subset of B and B is a subset of A. And once you are done, tell us your conclusion that, okay, since A is a subset of B and B is a subset of A, then A is equal to B. You want to tell us that clearly at the end of the day. So in summary, we've talked about sets, which involve union, intersection, difference, and complement. We talked about logic, which has connectives like the or and kind of thing, and the negative. We've talked about contrapositive. We talked about De Morgan. Then we talk about quantifiers, which are universal, existential, negation, and order. Then we talk about applications, talking about boundedness, density, limits, and functions. And we talk about methods like translating, selecting proof strategy, and control variables. Now, this is pretty lengthy, but I think it's really foundational to the whole idea of real analysis. So with this, I finally come to the end of this video. Thank you so much for listening. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. If you have subscribed already, I must say thank you. But if you haven't, you don't want to keep missing on very juicy content I have going on here. So go ahead and subscribe. Thank you for subscribing. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. Of course, you want to take it a step further, you can become a member of my channel to get some special privilege. So click on join and join any of the membership levels you are interested in. So we can keep building this community together. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.